topic of my presentation is applications of some basic theorems introduced in undergraduate classes. There are many basic theorems which are introduced in undergraduate course in mathematics, have immense applications in various fields as well as in higher mathematics. I would like to discuss one such basic theorem today, that is known as equivalence theorem. And this equivalence theorem is based on a very simple idea known as equivalence relation. I wish to show how the idea of equivalence play important role, and basically it plays pivotal role in mathematics and beyond. Now the question is why we are choosing this particular theorem, why I have chosen equivalence theorem for discussion. The first reason behind it is we do not acknowledge the power of a concept when we easily conceive the idea behind it, and equivalence theorem is one such, and perhaps its indispensability in almost every branch of mathematics overshadowed by its obviousness. The second reason is that the idea of equivalence theorem does not require any previous knowledge except for the idea of basic set theory. Let us go back to our school days. If anyone asks what is a rational number, then anybody can answer that very easily, that any rational number is a number of the form p by q, where p, q are integers, q not equal to 0, and p and q are relatively prime. Well, is 3 by 6 not a rational number? Of course, yes, because if we cancel the term 3 from numerator and denominator, then we will get the number half, which obeys this condition. So, there are several numbers like 4 by 8, 5 by 10, 6 by 12. There are so many numbers which are actually equal to the number half. So, in other words, a rational number is a representative of a class of numbers. So, without explicit mention to equivalence relation, we naturally begin to understand which numbers are rational. Now, before we come to formalize definition of rational numbers, let us recapitulate the definition of relation and equivalence relation. If we take a set X and take any subset A of X cross X, then A is said to be a relation on X, and whenever I take two elements A and B from capital X, then they are related if and only if the pair AB is inside the set A. If the relation obeys three properties, if it is reflexive, symmetric and transitive, then the relation is called an equivalence relation. Now, for any element A belonging to capital X, if we take the set of elements B belonging to X which are related to A, then that particular set is called an equivalence class of A, and that is denoted by this box A. Now, we formalize the definition of rational number in terms of, in the language of equivalence relation. If we take the set of integers z, we define a relation on z cross z minus 0 by the rule that the pair AB is related to CD if and only if AD is equal to BC. Then the equivalence class is denoted by A by B, and that is a rational number. Now, we get the formal definition of rational number as an equivalence class. So, now we can apply this technique of construction in case of any abstract integral domain. As we know that set of integers forms an integral domain and rational numbers form a field containing the integral domain Z. In fact, it is the smallest field containing the integral domain Z. So, applying a similar technique, we can get the field of fractions from an integral domain D. We can also use the localization of a commutative ring A with identity at a prime ideal P. Now, let us look at this example little more. What do we mean by localization? Suppose we are commutative ring A and identity element 1 is there in the ring A. Suppose P is a prime ideal on A. Then we take the set S, which is the collection of all elements x belonging to A which are not in P. Of course, this set has two properties. Since P is a prime ideal, it has to be a proper ideal, and therefore, one cannot be a member of P, and therefore, one has to be a member of S. And if we take two elements A B belonging to S, then the product A B is again a member of S, because P is a prime ideal. That means an ideal where we have the property that whenever the product is inside P, either A or B has to be inside P. Well, this set S is called a multiplicatively closed subset of A. And now we define a relation on the set A cross S by the rule that AS is related to BT if and only if AT minus BC into U is equal to 0 for some U belonging to S. This is an equivalence relation, and this equivalence relation gives us the equivalence classes which are taken inside AP. Now, this AP can be transformed to a ring by defining addition and multiplication very naturally, and that ring has a very special property that it is a local ring. Now, what do we mean by a local ring? A ring where there exists exactly one maximal ideal. Now, this example says that if a ring A is taken and the ring has more than one maximal ideals, then also by localizing the ring at some prime ideal, we can reduce the number of maximal ideals and get a ring with exactly one maximal ideal. So, equivalence relation provides a technique to reduce the number of objects obeying certain property. Among several other situations, I would like to address today two wide class of problems. One type of problems is called classification problem, and the other type of problem I name it as constructing new objects from old. Before we come to the first type of problems, let us state equivalence theorem and its converse first. The statement of equivalence theorem is the first one. It says that every equivalence relation on a set X partitions the set into disjoint equivalence classes. Actually, whenever I am given two elements from X and I have an equivalence relation on X, the classes A and B, they are either same or disjoint. So, from this basic property of equivalence class and also from the observation that the equivalence relation is reflexive, every element A of X must be inside the class A. So, from these two observations we get equivalence theorem. Now, the converse states that whenever a partition of X is given, we can always get an equivalence relation on that set X, and each equivalence class corresponding to that partition will coincide with one of the partition elements. So, now look back to our first type of problems, that is classification problems. Informally speaking, classification problem addresses how objects can be classified using certain property of the objects. Suppose we are given two objects, one is a green triangle and the other one is a red disc. If we classify the given objects, then whether these two will be in the same class or not depends on the particular equivalence relation. It depends on the attribute by which we are classifying. What do we mean by that? If the attribute is the color, then both of them will be in separate equivalence class. But if we take the attribute whether they are topologically same or not, then they will be in the same equivalence class. So, no matter what objects we are considering, our aim is to partition the collection into disjoint union of sub collections of the given class. Now, these are a few examples of classification. Suppose we are given all triangles in the plane R2. Two triangles A and B are taken from this collection. They will be related if and only if A and B are congruent to each other. Now, here the attribute is congruence of triangle. Instead of that, we could have chosen similarity of triangles to classify. If we are given a collection of sets, then we can use the relation whether or not two sets are in bijective correspondence or not. So, these are a few examples we can take as classification of a given class of objects. Now, the question is why we are so keen in classifying things. Two objects lying in a same class may not be equal, but they are equivalent with respect to certain property. So, if we classify the collection and choose one representative from each class, then studying one representative is sufficient, because they will have the same property if they are in the same class. This idea can be used for computation purpose also. For example, classifying infinitely many objects into finitely many classes helps to write an algorithm using the set of representatives. Now, let us cite an application of this classification problem in practical field. One application is component labeling. It is used in picture analysis, graphics and digital image processing. Now, I give two examples of component. The first one is like suppose we are given a picture P defined on a grid G and a pixel P is taken from the grid G having the value capital PP. Now, we say that two pixels are related if and only if PP is equal to PQ. Then this will be an equivalence relation, and this equivalence relation gives us equivalence classes which are called component, and these components are used for picture analysis. Another such example of component is connected component. What is that? Suppose a pixel P as shown in the first diagram is given on a grid G and there are 4 dots in the first diagram. If another pixel Q lies in one of these 4 dots, then that particular pixel Q is said to be 4 adjacent to P. Now, suppose P and Q are 2 pixels in a grid, they may not be adjacent. If there is a sequence of pixels P1, P2, Pn such that the first pixel is P and the last pixel is Q, and any 2 consecutive pixels are 4 adjacent, then we say that there is a path from P to Q as shown in the second diagram. Now, we define a relation that P and Q are 2 pixels, they are related if and only if there is a 4 path joining P and Q. This is an equivalence relation, and the equivalence classes are called connected component. Now, we come to our second type of problems, that is construction of new objects from given one. We explored this type of problem with the help of topology. Suppose X is a topological space, we define a relation on this set X, say capital R, and the equivalence classes are collected in a set called X by R. We can readily get surjective function which maps X, an element of capital X, to its corresponding equivalence class which lies in X by R. Now, the largest topology on X by R that makes the function continuous is called quotient topology, and the space thus formed is called quotient space of X. So, changing the relation, we get various quotient spaces from a given space X. Let us give one example of quotient space. Suppose we are given a rectangle. The rectangle is given here that capital X is equal to all the points x y belonging to R2 such that x lies between 0 and a and y lies between 0 and b, where a, b are real numbers greater than 0. Now, if we take a partition, as we mentioned earlier, that any equivalence relation is synonymous to a partition. What do we mean by that? Suppose we are given a relation, equivalence relation, we get a partition from it, and from a partition we can always get an equivalence relation. So, given a partition, we can always get an equivalence relation. So, in this case we are giving a partition of this rectangle. What is this partition saying? That if we take any point from interior or the horizontal edges, then those points are taken as a singleton in the quotient space. But if we take the points 0 y and a y, that is on the vertical edges, they are clubbed inside a single class in the quotient space. So, that means geometrically we are gluing the vertical edges of a rectangle so that we get a cylinder. So, that means cylinder is coming as a quotient space of a rectangle. Now, if we change the relation, if we instead of gluing the vertical edges directly, if we glue the vertical edges, but in a different direction, then the new quotient space formed is a Mobius band. So, there are many more quotient spaces one can get from a rectangle. Now, we come to another equivalence relation which is very important in practical field, that is called congruence of integers. Suppose a set of integers is given, two elements a and b, two integers a and b are related if and only if a minus b is divisible by a number k. Then this is of course an equivalence relation, and these equivalence classes, when we collect, we call that set zk. There are only k many elements in the set zk, but as we know, set of integers has infinitely many elements. Integers has the property that it is an integral domain, and zk thus formed is a commutative ring with identity in general, not in general an integral domain, but if k is a prime, then zk will be an integral domain. This particular relation of congruence of integers has many applications in practical field. Among various applications, I just mention one or two. The first one is hashing function for computer memory allocation. A common hashing function is as shown here, where m stands for the number of memory locations and k is the key of the record to be kept in the memory location. The second one is pseudo random number generation. Now, we all know that random numbers are very important, and especially in computer simulation we use random numbers. But once we want to generate random number by some systematic method, that is not random in its true sense. So, that is why we call it a pseudo random number. Now, to generate pseudo random numbers, we use congruence. The next one is check digit. We all are very familiar with barcodes shown in any retail product or any book. What is a barcode? A barcode is actually some numbers. In case of UPC, that is Universal Product Code, it consists of 12 decimal numbers, digits, and in case of ISBN, International Standard Book Number, has 10 decimal digits. The last digit in both the cases is called a check digit, and this is determined by using congruence. Now, why this check digit is there? It actually determines whether the barcode is correct or not. In case of UPC, the congruence is taken as this one, and in case of ISBN, the congruence is taken as this one. So far, we have discussed the power of equivalence relation, and the idea of equivalence relation is very simple, but it is used in so many different fields of study. That shows its power. Now, I would like to conclude today by showing another very important role of equivalence relation in a sophisticated theory known as rough set theory. Rough set theory was initiated by Z. Pollock in 1982. It was published in a journal called International Journal of Computation and Information Science, and it is very, very important today for managing uncertainties involved in incomplete information. Rough set theory is used in various fields, various sophisticated areas like data mining, intelligent control and data analysis. I give one or two examples of the application of rough set theory. Rough sets are used to find minimal sets of data called data reduction. Rough sets provide efficient algorithms for finding hidden patterns in the data. Actually, it is used to generate the decision rule which describes the hidden pattern inside a data. Rough sets are used for finding out whether the data is significant or not. But the thing is that so sophisticated tools are actually relying on the simple idea of equivalence relation. So, let us go back and see what is the definition of rough set. Suppose a set of objects is given called the universe U, and suppose capital X is a subset of U. An equivalence relation is defined on the set U, and that partitions U into disjoint equivalence classes. Now, we collect the equivalence classes. This collection of all equivalence classes is denoted by this one, and if we take the union of all the equivalence classes which intersect the set capital X, then that union is denoted by X upper star called upper approximation of X. And if we take the union of all the equivalence classes which are inside the set X, then that is denoted by X lower star and called lower approximation of X. Let us look at the diagram. Suppose capital X, the set, is drawn in red. We have some equivalence relation defined on that set X, by which we get the lower approximation of X as the rectangle drawn in blue inside that set X, and the upper approximation, that is the X upper star, is drawn in yellow. So, instead of taking the set X, we are taking the sets X upper star and X lower star for the representation of X by its rough set. Here are a few references which I have used to prepare this presentation. The first one is the book of Armstrong, where we can find quotient topology. The second one is the paper on rough sets, the introductory paper, and several other references were used, including Wikipedia, where we get so many applications of equivalence relations. So, these are a few glimpses of the power of equivalence relation. It shows that a simple idea can also play a pivotal role, and that may be very important in our, not only in mathematics, also in any practical day-to-day life. Thank you.